Welcome again, ladies and gents, to another flipped lesson. Today our focus is going to be on understanding what these letters Ka and Kb represent. So if we review what we learned earlier in the week, if I'm a strong acid, that means I fully ionize in water, so I have a lot of ions present. If I'm a weak acid, I do not fully ionize in water, so I have more molecules of my acid together than I have my ions broken apart. So what this means is in a strong acid, your forward reaction dominates, and in a weak acid, your reverse reaction dominates. And because of that, what we can do is we can write equilibrium expressions just like we did in the last chapter. So if I'm an acid, what we would do is we would write the equilibrium expression that we call Ka. If we were talking about strong and weak bases, we would simply call it Kb. So how do we write a Ka? It's exactly like what we did in the last chapter. It's products over reactants. So I would have my Ka, my products are aqueous, so I can include them both. So I have the concentration of my hydronium ion times my generic anion all over the concentration of my acid. I don't include water, remember, because it's a liquid. I only include aqueous and gaseous things in my equilibrium expressions. I can do the same thing over here for my weak acid. In this case, I still have my hydronium ions. My generic ion in this case is a B-, and it's going to be all over the concentration of my acid, which we're showing by Hb. So just like we learned in our equilibrium chapter, the actual numerical value for our Ka can tell us if we have more reactants or more products present at equilibrium. So we can put in numbers to numerically quantify whether we have a strong acid with more products present at equilibrium or a weak acid where we have more reactants present at equilibrium. So how would we write one of these things for an actual chemical equilibrium? So here we have our equilibrium for acetic acid, which is just vinegar. Remember, we don't include water because it's a liquid. So we would write our Ka is equal to the concentration of our products. So this would be our acetate ion times our hydronium ion all over the concentration of our aqueous acetic acid. And just like with our equilibrium chapter, whether our Ka is larger than or smaller than 1 tells us what we have more of present at equilibrium. So weak acids are going to have small Ka values because we know that weak acids exist more as molecules than ions, so our reactant numbers would be larger than our product numbers. Strong acids would have a larger Ka value because they do fully ionize at equilibrium. So we would have more ions present than we have molecules present. Page 647 lists a bunch of your different Ka values that we'll be using throughout the chapter. One thing to note is if you have polyprotic acid like H2SO4, because this thing ionizes in steps, what you'll have is you'll see multiple Ka values based off of which step you're starting on. So you'll notice that you'll see a Ka for H2SO4 and you'll see a separate Ka for HSO4. Since these things ionize in steps, each ionization gets its own Ka value. So what we define Ka as is it's the acid dissociation constant. And all that tells us is the ratio of ions to molecules at equilibrium. So it's just a new application of the idea of KEQ. Tomorrow what we're going to do is we're going to actually put some math into these types of problems just like we did in the last chapter. So go ahead and take a second to fill out that Google form and let me know if you have any questions. Have a great night, guys.